Bismillah, sallallahu Rasulullah. Okay, this course is gonna take me longer than I thought. Maybe 2 months to 4 months. Because it takes, lot of, I don't know. But it's not like a course on Khan Academy or Free Code Camp where your progress is being tracked, the material is being divided on several sections, etc. You have to do it yourself. You have to watch the course, the lecture, go back to the readings. The readings are long, and then do the exercises yourself, do the checking yourself. Nothing is easy in this course about taking a course, an old course from the MIT Open Courseware. Without further ado, let's finish with our problem number 6. So this is going to be problem number 6 from the first problem sets. We did case 1 and case 2. Let's do case 3, maybe 4, finish them, I don't know. But I have a lot of things to do today, so I'm not going to be spending so much time on it. The other courses are much more important than this course because finishing them sooner is gonna grant me access to places where I can at least make some amount of money to finance my life. So let's start. So where we have been, case 2, case 3. Case 3, made this number 5, problem 6. By case analysis, we took case 1 and case 2. Now we're in case 3. Of course, we case in case 1. So case 3, what does it say? Wx and r even, y is odd. So hopefully this will be quick. Yep. So we'll go from there. I think it's gonna be quicker. Okay, so case 3, W, Y. What does it say? Case 3, W. No, actually, case 3, Wx are all even. W. Now Wx are even. Y is odd. Wx are even. Y is odd. Okay. So what does the formula says? What does the theorem says? It says w squared plus x squared plus y squared equals z square. So it says w square plus x square plus y square equal z square. But what did we do exactly? What is this? We said here w, x, y are all even. W is even, x, y are odd. W, x are even, and y is odd. Okay. Did we cover everything? Wait. What are we covering here? W are all even. W is even. X, Y are odd. W, X are even. Y is odd. Okay. Let's not. Okay, so we're gonna go. Therefore, are even 2a square plus 2b square plus 2c plus 1 whole square equal z square. Okay, so this will give us wait, this will give us 4a square plus 4b square plus, here we'll say, first of all, what did we say? A plus b square equal a square plus 2ab plus c squared. So what we're gonna have is plus 2c square plus 2c plus, not plus, and 2 multiplied by 1 plus 1 squared. So it's going to give us 4a square plus 4b square plus 4c square plus 4c plus 1 equal z square. So what are we going to do with this? Yep. Easy. I think it's easy one. So we're gonna take common factor for a square plus b square plus c square plus c all plus 1 equal z square. Therefore, every even number multiplied fuck off. Multiplied by a number then added 1 is odd. Therefore, z square is odd and only odd numbers are squared to be odd. Theory holds in this case. So, okay, yeah, don't. Okay, nice. The algebra here is all correct. Good catch fixing that. That's exactly the mistake from case 1, now correctly written out. Let's check the chain. This is right. Case 2, remainder of 2. That's a real. That's a real achievable remainder with lands here. So this case generally has a valid solution, different flavor of conclusion than case two's impossible outcome. Two things to tighten your closing. You concluded Z is odd, but stopped there. The theorem is about Z's parity, not Z's square. You need one more sentence. Since only odd numbers since only odd numbers square to odd, Z itself must be odd. You have the right fact stated, just need to explicitly apply it to Z, not just Z squared. Theory holds in this case is vague. Say why it holds. The theorem claims Z is even, Wx, y are all even. Here Wx are even, but y is odd, so it's not the case that Wx, y are all even. Consistent with that, you just showed Z must be odd, not even. That match is what makes the theorem hold, worth spelling out explicitly the same way you'd want it clear in case 2. Fix those two lines in case 3 is solid, want to adjust wording. Oh my god, baby, you make me work. Make me work. So, I'd add one thing only. Seriously. Therefore, theory holds in this case. It's obvious. Then added 1 is odd, therefore z square is odd, and only odd numbers are squared to be odd. Therefore, theory holds in this case. Because z is odd, not even. Oh my god. Oh my god. Not even. How about now? I flagged one small bullish note. Right now the sentence odd numbers are squared to be odd. Theory holds in this case because z is odd, not even. That makes it read like theory holds. It's concluded before you even say that. I know you would have said, I knew, I knew. But I am too lazy. Fuck. How about now? How about now? Like it now. As is good that closes out book. So you're feeling lazy today, that's totally fine to leave as the math holds together. Want to keep going at case 4? Yep. Let's go to case 4. They're all odd, huh? Case 4. Are all odd. WXY are all odd. Okay. W, X, Y are all odd. So what we have? W squared plus X squared plus Y squared equals Z squared. Therefore, 2A plus 1 all squared plus 2B plus 1 squared plus 2C plus 1 all squared equal Z squared. Therefore, it's gonna be 2A squared plus 2A plus 1 plus 1 squared plus 2B squared plus 2B 1 plus 1 plus 1 square. Don't forget the 1. And that's it actually. Here's where you make little mistakes. Come on. Maybe. Plus 1 square, it's already finished here. So 2C square plus 2C 1 plus 1 squared. Therefore, this goes 4A squared plus 4A plus 1 plus 4B squared plus 4B plus 1 plus 4C squared plus 4C plus 1. We'll go, how many ones do I have? We'll go take a common factor as the 4, which will go, therefore 4A squared plus A plus B squared plus B plus C squared plus C all plus 3 Z squared what did we say in number 2? Case number 2. for Z to be either odd or even, LHS must be a remainder of 1, must has a remainder of 1 or 0, but here it is 3, therefore proposition holds. So what we're gonna say is therefore for Z square to be even or odd, the left hand side must have a remainder of 1 or 0, which means that Z is neither odd or even, therefore theory holds in this case. Okay, that's case 4. What about now? Okay. Clearly, neither. This isn't actually the correct conclusion. It's worth questioning why. Even integers is either odd or even. Every integer is either odd or even. There is no third option. So Z is neither odd or even can't be valid outcome of an integer. What you've actually shown is different. Since squares can only either leave a remainder of 0 or 1, 4, never 2, never 3, and here Z would need to leave a remainder 3. That's impossible for any integer square. So the correct conclusion is about Z's parity at all. It's that no integer Z can satisfy the equation. In this case, same situation as case 2, not Z is some weird non-parity thing. But this case has no valid solution at all. This matters because it changes your closing sentence. Instead of Z, it should be something since no integer square leaves a remainder 3. Mod 4, no valid Z exists in this case, therefore it's I hate this, consistent with the proposition. Okay. So which means that Z is have a remainder, which means that there is no valid answer for Z to be even. Therefore, prop holds here. Come on. Come on. Oh, fuck off. Yeah. Good, you fixed the conceptual point, but the wording is now slightly off. A different way. You wrote there is no valid answer for Z to be even. This makes it sound like Z could still be odd, not even. That's not what you actually proved. What your algebra proved is Z would need a remainder of 3 mod 4 and not a no integer square can ever give a remainder 3. Squares only ever give a remainder 0 or 1 as you established, so there is no valid integer Z at all, not just no even Z, but no Z of any kind or even. So the fix is small, but matters. Instead of no valid answer for Z to be even, it should be something like, which means no integer equation. Therefore, this case, the solution the proposition holds. Command C. Okay. Okay. Let's move on. Case 4, case 5. Got no time for this. Where is case 5? Case 5. W is odd, X, Y are even. I think we've been here. W is even, X, Y are odd. I think we've been here. So do we really need the other two cases? Because they are the same. I mean, the only difference is that the letter changed. 2. You know, hey, you're into something real, but let's be priceless about actually the same versus what's just superficially said, because that distinction matters for whether you skip the writing. Looking at your case list, compare case 2, but compare case 3 to case 6. Wait, these also differ. Case 3 has 2 evens, 1 odd, has 2 odds, 1 even. What do you mean? 2 odd, 2 even. 2 even, 1 odd, 1 even, 2 even. So here's the real question. Does the algebra actually only depend on way, even odd, not on which specific letter? Which if you look at your case algebra, would it matter if you instead doesn't care? It doesn't matter because it's a plus. Since addition doesn't care about the order. So your instinct is right for a specific reason. The number of evens terms determines the mode, not which specific variable plays which role. That means exactly 1 even to odd only needs to be checked once. Exactly 2 even 1 odd only needs to be checked once. Since case 2 and case 3 both have exactly 1 just different variables being even, the algebra is structurally identical, only the labels differ some for case same for case 3 and case 6 exactly 2 even. So yes, you can skip 5 and 6, but only if you say so explicitly. You need one sentence stating by symmetry the cases where exactly one of regardless of which variable all reduce the same computation as case 2 and similarly for 2 even cases, case 3, this sentence is what makes skipping legitimate. Silently skipping without nothing look like you missed the case. Want to write the symmetry to close things out? Okay, so so for case 5 and 6, and since case what 2 and 3 صح since case 2 and case 3 has already ha ha motherfucker handled two odds and one even and two even and one odd and in the case of addition, it makes no difference to change positions positions and positions. Therefore, proposition holds in all cases. So do this. And honestly, a nice piece of reasoning. You've correctly identified it's the commutativity. Order doesn't matter. That lets you skip the reliable case. It's a legitimate, well-justified symmetry argument. Full proof for problem 6 is now complete. Case 1, 2, 3 fully work. Case 2 and 5, 6 justified by summary. All 4 distinct outcomes covered, which lines up correctly with the theorem in every case where hypothesis is satisfiable. The conclusion matches. Nice work pushing through this one. It took real digging, but parity mode for symmetry, but the final proof is solid and legitimate, not hand-waved. That's genuinely good problem. So where are we at? The daily, I think, discrete math. We're done with the lectures, complete course notes. Let's go for what are we having? No, assignments. Sets 2. Desktop. MIT. Okay. Red Claude. is do you see anything here with regard chapter 2? Chapter 2 also. Chapter 2 because I think we finished the problem set 1, problem sets 1, problem sets 1. Where is it? Assignment 1. We finished it. It's 6 problems. 6 problems. We finished 6 problems. Good question to check before diving. Let me map this out. Since it matters for what you can tackle right now versus needs more reading first. Chapter 2 actually covers, which you've now finished, section and sets. The axiomatic method by case providing applications that proving ifs, proof by contradiction, and proofs about sets. I didn't. What chapter 2 does not cover induction and the well-ordering principles are chapter 3 material. This document doesn't include them at all. This document doesn't include them at all. Now looking at problem 1, 2, 3. Problem 1. Application proof part 1. Part D implicitly says proof by coordinate. This is fully chapter 2 territory. Have everything you need. Problem 2 is proof by will ordering, will or induction. Not chapter 2. You haven't read this technique yet. Problem 3. The hint explicitly says induction of the number of time steps, not chapter 2. Before asking you to find in a bogus induction proof, not chapter 2. You need to know how induction to work to spot what's wrong in this. Problem 5. Proving a formula for recursively defined circle is a classic induction problem, not chapter 2. 6. A, D are mostly direct proofs, chapter 2. But part E explicitly built on invariant argument, which is really induction, but reasoning, even if not labeled as such. Doable. So A, D doable now. E, F shaker without induction. Problem 7. Induction, not chapter 2. Problem 1 is fully within reach now. Part A, R2, everything. Wait. I have not read. Wait. I have reached sets on chapter 2, not read it or the rest of the document. Still. Oh, God damn it. Which accounting effects now not green, so your action position you've read. Proof. About to start proof. 2-7 are still ahead of you. Direct implication coordination, fully within what you've read. Problem 6, part A. Ask about order of tasks, continuous Effective moves on bright, mostly direct proof, no sets needed, also within reach. Problem 6, EF and everything else still blocked, but now for the same reason as they they need induction chapter 3, which is separate from read 2, 6. So nothing changes about which problems are reachable. Problem still within your reach. Okay, wait. I want you to check lecture 2. Lecture 2. Induction. It is induction, but it says induction. Covering proof by contradiction and induction. This is on the inductive techniques in proof by induction. Does it include chapter 2? Don't fetch, I'm telling you the truth. It's not really chapter 2 content in the text. Here's the actual map. By contradiction, this is chapter 2 to 5, which you've already read. Lecture 2 likely just briefly recaps it before moving. Induction, this is chapter 3. Material in the textbook, not what you upload, then it is the main focus. So lecture 2 is really the video companion to 3, not chapter 2. It's the next chapter's material delivered as a lecture. Watching it would actually be a great move right now, since it's exactly the tool you're missing for problem and 6EF and BS2. Given that, a sensible order might be problem 1 now. You're ready. The problem 6 AD now. Direct proofs. You're ready. Watch lecture 2 to get action. Come back for the rest. So is chapter 2 in this lecture. Yes, based on that description, lecture 1 lines up closely with chapter 2 plus a bit of chapter 1 on that description closely with chapter 2 plus chapter 1 review. Here is axioms and propositions. Truth chapter 1 she covered earlier. Discrete math problems. Clear quick recap. Implications. 2 point. Only an implication. Direct and contra. Direct. Spy. And conjugate. Like Goldbach. Multiple consonants. 3 as motivating example. So lecture 1 is essentially a diversion of what you've already read. 2.12 and the truth table. Chapter 1. It won't cover proof by contradiction. 2.5 or sets 6 based on the title split. Those likely showed up as the contradiction portion mentioned. Tier 2 description instead. If you've already read through 0.25 like you said, one would mostly be spent reviewer could still be useful. Right. Lecture 1 is what I watched, but it's hard to tell whether or not it covers our chapter 2. So I did read it anyway. Now I am asking so that I know whether I should watch lecture 2 before proceeding with sets and the rest of chapter 2. Good catch to push on this. Good catch to push on this. And I should be upfront. I was inferring where contradiction sits based on two titles, not confirming it by action. That's meaningful difference, and it's worth being honest rather than letting you a study plan on a guess. Here is what I can say. Confidence versus what is speculation. Comfort from the description themselves. Lecture 1 description explicitly mentions axioms, propositions, truth tables, implications, famous conjectures. Lecture 2 explicitly mentions proof by contradictions briefly and induction main focus. What this leaves genuinely uncertain. Whether 2.4 proving if and only if gets its own lecture coverage anywhere or is it as reading on. Whether sets 2.6 is covered in any lecture or is purely textbook material with due counterpart. Exact boundary of what's briefly touched is taught in depth in each lecture. Descriptions are summaries, not transcripts. This is actually an important general reason for approaching this course. Lecture descriptions and textbooks chapters don't map one to one. Courses like this often mix reading only sections, things you're expected to absorb from the book, no lecture, with lecture only asides. Examples or motivation not in the book, trying to force strict co- correspondence between chapter X equal chapter lecture Y. You can waste time chasing a mapping that doesn't fully exist. Practical suggestion than me guessing further, you could open the actual lecture transcript. There is a link on search for contradiction if that'll tell you definitely. So going back, actually do. Lecture 1 maps to 2.1 to 2.4. Applications. Chapter 1 does not cover 2.1 or sets at all, whether a contradiction shows up lecture 2 alongside. There, something I haven't verified. I need the transcript to be sure rather than trusting the summary blurb again. To put lecture 2 transcript the same way so we're not guessing on the Proof by contradiction recap. The two examples essentially the same proof. Proof by contradiction. Okay. Dash, mais, 13, 14, 16, 17, 17, 18, 19, 20. اوكي سو 1 2 3 4 5 6 7 9 10. Okay then now I could say that I fully covered lecture 1, which means lecture 2 will be next on another day though. Okay, let's Let's see how long that took me. How many problem sets there? How many lectures? 24 of 25 lecture. And the problem sets, the assignments, 12. Lecture 1, 13 days ago. On problems 2. So go to my YouTube channel, 13 days ago. So, what do you think? "13 days to fully own lecture. One's worth of material, genuinely not slow, especially given everything else in the mix. Tell up what happened in that fancy reading. Thus this wasn't your only thing running. So this isn't how fast should I be going. Charge official base per lecture number to compare against. The students taking this in person have it as one of several courses, with recitations, TAs, and no need to also build freelance profiles. So brand on this side, comparing your self-directed base to that isn't really apples to apples. The depth was real, not padding. M6 alone took you through several moments, quadruples, visual symmetry. I want to ask you. It's not, or is that actual concept only, which is already sort of the point a few days ago. 13 days for lecture 1 doesn't predict 13 days for lecture 2. Lecture 2 is heavier, induction is the most technique in the course, per the professor himself. but you're now warmed up on proof match mechanics in a way you weren't 13 days ago. If you want a genuinely useful number to track, it'd be less days per lecture and more actually understand and can I redo this without help, which based on today's can for contradiction and case analysis. That is the metric that matters. Oh baby. Wait. There is only 12 problem sets for 25 lectures. So I really do not know. Good thing to flag, and honestly, oh shut the fuck up. 520. Okay, that'll be it for discrete math today, you guys. See yous.